So Reshma did a fantastic job of talking about the electrocatalytic side of things, and now I'm going to tell you about the photocatalytic side of things. So this is what I'm going to go through in my talk. A short overview of the origins of pump probe spectroscopy. Then I'll go and explain what photocatalysis is. Then one branch of photocatalysis, photoelectrodes, and how they work and how we can measure their performance. Then I'll give you some examples of transient absorption spectroscopy. So this is one type of the pump probe spectroscopy that can be used to understand photocatalysts and photoelectrodes. So I'll give you what a typical setup is, how we can understand the spectra that we get from them, and give some, as I said, go through some example materials. And then another type of pump probe spectroscopy, photo-induced absorption spectroscopy. I'll again give you what a typical setup looks like and some example cases. So pump probe spectroscopy, what is it? Otherwise known as flash photolysis. It was developed in 1949. So my understanding was just after World War II, they developed these, or they tried to develop cameras that could photograph missiles in flight or like fighter jets in flight. And in these cameras, they had these flash tubes that could really powerful flash tubes. And this technology didn't really work out like they wanted it to. But then Porter realized that these high intensity flash tubes could instead be used to study really fast photochemical reactions. It's a very fast pulse of light. So Egan, Norrish, and Porter developed this flash photolysis technique in 1949 and were later awarded the Nobel Prize in Chemistry. So essentially what you have is a really fast, high intensity pulse of light, like a narrow pulse of light. So in these flash tubes, it was on sort of the millisecond time scale, the width of this pulse. And then you excite stuff with that light, and then you then probe what you've just excited and see what happens after you've generated all of these excited states. And you can probe these things in different ways, which I'll explain later. And then later on, or much later on, in the late 90s, Zavale won the Nobel Prize in Chemistry for basically further developing this flash photolysis technique. So when we developed lasers and new optics, we could get much larger gains in time resolution, pushing it from like the millisecond to the femtosecond. So then we could start understanding really fast timescale processes. So the femtosecond is essentially when you have the absorption of light and the initial generation of your excited states, to the millisecond where typically catalysis takes place. So you could look at the whole spectrum of what is going on. So you can see it's a very important area of science because we've had two Nobel Prizes in this topic. So it's good to understand, even if you don't work specifically in the area of flash photolysis or use it at all, it's good to understand its merits and what you can do with it. So what do people do with it? So they study a whole range of different things, so from organic molecules and polymers to nanoparticles, semiconductors, lots of sort of man-made stuff, which we can use in like photocatalysts or photovoltaics. And also we can look at biological stuff like plants and other biological systems to study photosynthetic processes or light-induced changes in conformation and this kind of stuff. So you can study a lot of things. And like I mentioned earlier, it depends on how you probe it. So it's a pump probe spectroscopy. So you can use, essentially you need to look at what different areas of the electromagnetic spectrum to see what's going on. But what Reshma showed in her talk is that it depends on which area you probe in. So if you probe in the low energy region, you see different things. Like she showed, okay, if you look in sort of the radio wave region, you'd see different nuclear spin interactions. But then if you go to higher energy, subsequently, maybe it's rotations, then vibrations, and then in the UV region or visible region, it's electronic excitation. So you can look at all of these different perturbations that are induced by your initial pump and how it affects your system. Okay, but the focus in this lecture today is not to go through all of the different types of pump probe spectroscopies, because that lecture will take forever. I'm just going to focus and really hone in on photocatalytic processes, specifically for water splitting using semiconductors. So what is photocatalysis? We need to know what photocatalysis is before we can really dive into this lecture. Essentially, it's the acceleration of a photoreaction in the presence of a catalyst. Okay, that is what photocatalysis is. From the name itself, you'd probably get a bit confused. It's a bit of a misnomer because it implies that light is a catalyst, but it's not. It's not at all. It's a catalyst that sensitizes a photoreaction by absorbing light. That's essentially what is happening. And what makes it even more confusing, at least from my standpoint, is that you have two branches of photocatalysis. You have photocatalytic processes and photosynthetic processes, depending on the Gibbs free energy change of that specific reaction you're looking at. So water is a photosynthetic reaction because the Gibbs free energy is positive. So it's not a spontaneous reaction that would suddenly happen on its own. Water would not suddenly spontaneously form hydrogen and oxygen. So even though people refer to it as a photocatalytic reaction, it's actually photosynthesis. The most studied reaction, as I said, is water splitting of all of the different types of photocatalytic reaction. And the most studied catalyst is titanium dioxide. So how does this catalyst even work? Okay, so we need to understand a little bit about the material and its structure and its properties to understand how it can even do this thing, how it can even absorb light and use that energy that it's generated by absorbing light to drive the splitting of water into hydrogen and oxygen. So we need to look at the structure of the material. So titanium dioxide, the most common polymorph and active polymorph, is the anatase form, where we form these titanium 06 octahedra throughout the structure, which are slightly distorted. And these orbitals all interact. So this is a bit of chemistry. Maybe not all of you are chemists and you're not too interested exactly how this energy diagram arises. It's probably confusing you right now, but it's not too confusing if you really look at it step by step. Essentially, you have these d orbitals in titanium which interact with the surrounding oxygen ligands, okay? And they split in different ways depending on whether or not these d orbitals point directly at these ligands. So if they point directly at these ligands, they're high energy up here. If they point between the ligands, they're lower energy. If you think about simple electrostatics. And the orbital, the specific orbital, the dxy that points between these distorted oxygen bonds, so that they're pointing even less so that the other orbitals that lie in the z-plane, it's even lower in energy. So in terms of this empty band, because the titanium 3d orbital is d0, it's a titanium 4+ state, so it's got no electrons left in its d orbital. So this is the empty band that forms here. So I'm talking to you about things on a molecular level that would form these discrete energies. But once you have this very large crystal with, for all intents and purposes, an infinite crystal, or infinite number of atoms, then you form a continuum of states and you end up with these bands. And this band here, which is empty, is called the conduction band. And down here, you have these oxygen 2p orbitals that, again, they interact and they're field orbitals, and they form this p-pi state here, which is the valence band. And then this transition in energy from this field state here to this empty state here, that is the excitation of light. So you can promote an electron essentially from these oxygen 2p levels to these titanium 3d levels. And that energy gap between the valence and conduction bands is around 390 nanometers, and the positions, the energies of these different bands versus the normal hydrogen electrode are roughly here. And what you can see here with these dashed grey lines is that the water oxidation, the thermodynamic potential for water oxidation is around 1.23 volts. And we have this very large overpotential for the valence band to drive water oxidation. So when you excite an electron from this valence band to the conduction band, leave behind a positive charge called a hole, and that hole oxidizes water, or it can oxidize water. And this electron up here has sufficient energy to reduce protons, which lie at a thermodynamic potential of 0, to make hydrogen. And these are just the reactions that I've described. And we can see here that for TO2, you can only use light that is 390 nanometers or higher in energy, or lower in wavelength rather. And we'll see why that's slightly problematic in a sec. But before we go into that, I just want to highlight the first time that this was showcased, that titanium dioxide can work as a photoelectrode to drive water splitting. That was by Fujishima and Honda in 1972. And you can see here, it's been cited more than 20,000 times. So it's a very, very important piece of work, and simply how you can take a very cheap metal oxide catalyst like titanium dioxide, very easy to fabricate, very abundant mineral, and you shine a bit of light on it, and Bob's your uncle, you get hydrogen. So it's an amazing concept of how we can get very clean, renewable energy, but it's always more complicated than that. So what materials have been studied the most and why? So mostly titanium dioxide has been studied out of all of the different materials, but let's think first about the different classes of materials. So titanium dioxide is a metal oxide, and it's been studied the most. So these are the publications per annum, and we can see that it's been growing steadily over time. It's becoming much more popular over time. I guess that to do this work, it's becoming more accessible and it's becoming, with climate change, more imperative that we can develop cleaner ways of making fuels. So I guess that's why it's growing in popularity as well. But we can see other types of materials like nitrides and oxynitrides, or silicon and 3,5s. So these materials, in terms of their efficiencies for driving water splitting, generally can show higher efficiencies than metal oxides, but they're much less studied. And that the thing is that there are reasons for that. It's essentially because they're much more difficult to make, these materials, and they're much less stable. So when you place these types of materials in water, they tend to corrode. So when you place metal oxides in water, they're already oxidized, so they don't tend to corrode. Okay, and of the different types of metal oxides, which will be the focus of this talk, we can see that titanium dioxide is the most popular. Hematite, again, is quite popular, and bismuth vanadate, which was work was only started really in 2000 on this material, is really starting to surge in interest. But the problem with metal oxides is they have, in general, quite wide optical gaps. So we can see here, these are a bunch of different types of metal oxides, and these are relative percentages of light that they can harvest from the solar spectrum here in black. We see that silicon, which is a very popular material for studying water splitting, albeit they're stable than the oxides. It can use around 2/3, or it can harvest around 2/3 of the solar spectrum, whereas these metal oxides can harvest much, much less. If we take titanium dioxide, for example, it can only harvest around, the anatase form can only harvest around 3% of light, which is an issue. But if we compare it with silicon, it has a much larger thermodynamic potential or driving force for driving these different reactions, whereas silicon can only drive the water reduction reaction, but not the water oxidation reaction. So how do we understand or quantify the efficiency of a photocatalytic reaction? We can break it down into different parts. Okay, so the quantum efficiency, so how well it uses light to drive that process. We can look at the light harvesting efficiency. So simply you can just look at the absorption spectrum of your material. That's readily done by anyone, I'd say, with any spectrometer in a lab. But these three quantities here, how efficiently the charges separate, how efficiently these charges transfer throughout your material, and then how efficient the catalysis is, then these three terms, you require some form of time-resolved spectroscopy to understand how well each of these components are occurring. So let's see what a typical profile is for for reaction, okay, for photocatalytic reaction. So first we have light absorption in the femtosecond time, on the femtosecond time scale, and we get charge separation there. You have these maybe polar ionic interactions and trapping of these charges, which happen sort of the picosecond to nanosecond. And then over a very wide period of time, you have the possibility of recombination. So essentially, when you excite your electron from the valence to the conduction band, you have this caloric attraction, electrostatic attraction, that the electron just wants to fall back into the hole. I mean, why not? So this is always going to compete with the catalysis. So I mentioned earlier about the efficiency, how well these charges transport through the system. Well, yeah, they have to transport to the surface of the catalyst, where it interacts with, for example, water, if you want to think about the water splitting reaction, and then drive the splitting of water. So, and all these different processes that have to occur, as well as the catalysis, which can be, generally, it's very, very slow. It's on the millisecond time scale for water splitting reactions up to the second time scale. So if we think about it, there's a huge, several orders of magnitude difference between when we actually generate the charges and how they then transport to the surface and then drive the catalysis of the reaction. Huge differences. So if we think about this in terms of the origin of the universe, for example, so like the Big Bang, and we think about this time scale in minutes. So I think we're roughly on 10 to the 15 minutes since we've existed, okay? I mean, the universe, not us. I mean, I'm not that old. And then, so if we think of this time scale as minutes, we have to go back to the Big Bang. It's when we generate the initial excitation in your system, and then we have to wait until here 1 minute for the catalysis to occur. Okay, so it's a huge, huge time scale. Okay, and it's very difficult for systems to drive this reaction. If you have really slow catalysis, it's very difficult for you to drive catalysis efficiently when you have such a long time period between when the charge is formed and when it can actually drive catalysis. And that's why we see here, because of this discrepancy between when you can actually drive the catalysis and when the charges are formed, we see quite large recombination losses. And this example here is for an alpha hematite photoanode, very, very large recombination losses. Okay, and we understand this now because of time-resolved spectroscopy, and then we can figure out strategies to try and circumvent these deleterious recombination processes and enhance catalysis. So most people work on photoelectrodes. Like I mentioned before, the Fukushima and Honda effect was using a photoelectrode. Essentially what a photoelectrode is, it's nothing too fancy. It's just you take a photocatalyst and you affix it to an electrode. Either you can grow it directly on the electrode or affix it some way. Okay, so this is just a simple definition of what a photoelectrode is. It's essentially a photocatalyst on an electrode that uses light to drive electrochemical transformations. Okay, we show an example here on the right of a photoanode. How am I doing for time, by the way? 15, okay, plenty of time. Okay, so here I show an example for a photoanode. Okay, so the photoanode can drive oxidation processes, and photocathodes can drive reduction processes. Okay, I'm just showing an example here for a photoanode because most metal oxides form photoanodes, but given their N-type semiconducting nature. But you can easily just reverse case whatever I say coming up for a P-type photocathode material. So what you have is you normally grow, it could be a nanostructured material, but let's just take the simple case of a flat material that's grown on an electrode. Typically it's a transparent electrode so that light can come through it either from the back or the front. Here we show a large area hematite photoelectrode that's been grown by the Hankin group and then studied for its photoelectric catalytic water splitting. And yeah, so you can grow it on a transparent electrode like fluorine doped tin oxide on glass. This could be the hematite layer here. Typically it's just a few 100 nanometers thick. And before you apply a potential or anything like that, you have a Fermi level in your material, and you have a redox potential of the electrolyte, in this case water, and these things will want to equilibrate. And when they equilibrate, essentially you'll get a flow, or typically what you get is you get a flow of electronic charge from your material into the electrolyte, because normally the redox potential of your electrolyte is lower in energy than the Fermi level of your N-type semiconductor. So you get a flow of charges from your semiconductor into the solution. And when that happens at the surface of the material, you get a region of net positive charge. And that region of net positive charge is called the depletion layer, or the space charge layer. And because you form this region of positive charge after the equilibration of the Fermi level and the electrolyte, then you get this preponderance of negatively charged ions from the electrolyte. For example, in water, it could be like hydroxides. You get a preponderance of hydroxide ions localized on the surface of your material. Okay, but essentially, if we want to care about what's happening in your photoelectrode, because of this charge transfer and this buildup of positive charge at the surface, we get a bending of the bands of these energies, these conduction bands and valence bands. And this bending, in the case of an N-type semiconductor, it drives electrons to move towards the electrode, electrons that form after being photoexcited, and holes to move towards the surface and drive oxidation processes. And this is essentially why an N-type semiconductor is really good at driving oxidation processes. So how do we study the performance of these materials? We typically use a 3-electrode cell, an arrangement shown here, where we have the working electrode where you place your photoelectrode, a counter electrode. Typically people use platinum. It depends on the chemistry that you're doing. But here, if we're going to look at water splitting, where the semiconductor photoelectrode is oxidizing water, it would be a good idea to use the champion material platinum here at the cathode counter electrode to drive proton reduction. And then we have here a reference electrode that can be used to determine the voltage relative to a reference when you measure the performance. So here in the bottom right, we have an example of hematite again. The orange is the actual performance, okay, and the blue is the ideal performance if we take the flat band potential of the material, okay, and if we understand how much light the material can harvest, okay, and how that can be converted into a current, it can achieve over 12 milliamps per centimeter square of current density using 1 sun of solar power. Okay, so what we can see here is that from the ideal curve, where we go from flat band and we start increasing the voltage away from flat band and actually start bending the bands like this, we don't suddenly get this shooting increase in photocurrent. We have this really long delay between the flat band potential and where photocurrent is actually observed in this material, and we never actually reach this ideal scenario where we get unity light harvesting. So there's huge differences between this point here and this point here, and essentially it's all because of what I said to you earlier, because of all of these recombination processes that are happening in this material. There are lots of problems in this material. And we can essentially break it down into 2 different processes. One is the recombination. How would you overcome recombination? By using a voltage to bend the bands sufficiently so that we can avoid electron and hole recombination by spatially separating them. So what you can imagine here is that if light comes in and is absorbed here, and we get an excitation of an electron from here to here, this electron will slide down this slide and go wee all the way over here, and this hole will go up the slide because electrons up here will fall into the hole, moving the hole upwards. So we get this really good separation of electrons and holes within the space charge layer. Okay, so if we apply more potential, so if we apply a positive potential and we pull this Fermi level down, 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 we get a much better bending of the bands, okay, and a much wider space charge layer. Okay, and that's what this term essentially is referring to, how we can avoid that by using potential to overcome the recombination component. But there's also this catalysis component. So once the holes actually are long-lived and at the surface, I mean, they need some overpotential, kinetic overpotential, to drive the catalysis as well. So how can we study these things? So we typically use transient absorption spectroscopy, and this is what a typical setup is like. So here S is your sample, okay? And nowadays we use lasers instead of flash tubes, like Porter did. So we use lasers because we have much narrower pulse widths to excite your sample. We have a series of optics to measure what's going on. So typically in transient absorption spectroscopy, we measure in the UV visible and sometimes near IR regions. We probe in those regions, okay? And here, for example, we have a polychromatic lamp that can emit in those regions, the UV visible regions. And we have a series of lenses to focus that probe light onto your sample and then through to a detector. We study the behavior at different wavelengths using a monochromator. Sometimes we use filters if the lamp can also excite the sample as well to get rid of any of that high energy light that could potentially excite the sample. The important thing is what's shown here, okay? So the black is a typical ground state UV visible absorption spectrum of a sample, a generic sample. But the green is what you would get when you photo excite the sample here and then see the absorption, okay? So the differential spectrum between the ground state and the excited state is shown over here. So you get this photo-induced absorption region. So when you excite the material, you generate a bunch of electrons and holes in the material. And those electrons and holes can absorb in the visible region. But then you lose the ability to excite charges from your ground state because the population of your ground state decreases. So that's why you get a bleach here. So let's go through the most commonly studied material, titanium dioxide. And this is just general, what the TAS kinetics look like of this material, probed from the microsecond, roughly the microsecond up to the second. And this is what the spectra look like at different time scales from 10 microseconds up to around 100 milliseconds, okay? And we're not looking at any process like water splitting, etc. We're just looking at, this is titanium dioxide in an inner environment. Let's just look at what the intrinsic electron-hole recombination behavior is like in this material. And we can see that intrinsically, charges recombine typically on the millisecond time scale, okay? So this is without any kind of band bending, etc. It's just a photocatalyst on its own, what it generally does. So the half time from the microsecond is around the millisecond. And we see this power law decay dynamics, which is characteristic of this particular material, because when you generate electrons and holes in titanium dioxide, the holes are pretty static. They have very poor mobility, but you have really strong mobility of the electrons, and they hop around throughout the material through these shallow trap states, and eventually they bump into a hole and recombine. Okay. So how do we understand this stuff? I mean, why do we have really strong absorption here in the blue and much less weaker absorption in the red, for example? Why is the spectrum shaped like this? Well, we can use computation to try and understand that. So, for example, you can use a cluster, titanium dioxide cluster, and you can generate, titanium 3+ states where you can essentially localize an electron, or oxygen 1- states, and look at these molecular states and look at their absorption behavior. And from that, you can also generate these transient absorption profiles from these different molecular states that you can form computationally. And what you'll see is that holes will generally absorb in this region, and electrons more so in the red and near IR. So this is the free electron component, this is the trapped electron component, and these are the trapped hole component. So you can use computation, or you can actually do experiment. So for example, you can use different types of scavengers, electron scavengers and hole scavengers, which get rid of most, if not all, of that one part of the signal, and you're left with the rest. So for example, if we have titanium dioxide nanopowder, for example, and we immerse it in methanol, which is a really good electron scavenger, the signal looks like this in red, okay? So we lose this strong absorption in the blue region. We lose that pretty much entirely, and we get much stronger absorption in the red. So what that indicates is that the electrons primarily lie in the red region of the spectrum, but it's a very broad signal, okay? Where there's lots of different types of energies that these electrons can possess, or states that they can feel. And then the same for silver nitrate, which is, again, a fantastic electron scavenger. So this positive silver ions can scavenge electrons really well to form silver metal. And we get a really much stronger absorption in the blue than before, compared to here, decreasing into the red. And what we can do is we can take what the typical absorption spectrum looks like, which is the blue, the black circles, okay? And then we can use these profiles to try and deconvolute what's going on in these signals, okay? Essentially, we can see that this part here in the blue is dominated by the holes, the hole signal, and this part here in the red is, it's mostly dominated by the electron signal, okay? And so, for example, if we probe the spectroscopy at around 450 nanometers or 500 nanometers, we can say, relatively speaking, we're looking mostly at hole carriers versus electron carriers. And that's what we're going to do now. So we took a titanium dioxide, we made a titanium dioxide photoelectrode. Okay, so we grew around a micron thick layer of anatase titanium dioxide on FTO glass. This is what the current voltage curve looks like, which is a measure of its performance. We can see here in the dark that we start to see electrocatalysis from around 2 volts versus RHE. So as electrocatalysts go, titanium dioxide it sucks, because we're about 0.8 volts above the thermodynamic potential for water oxidation. So we need around 800 millivolts of overpotential for this material to electrocatalytically start to oxidize water. Okay. However, in the presence of light, it's really good at photocatalytically oxidizing water. We see here from really low potential of around 0.2 volts versus the reversible hydrogen electrode, we start to get photocurrent, okay, which plateaus relatively quickly. So from around 0.7 or 0.8 volts, we start to reach its plateau photocurrent density, okay? And in this material, depending on the wavelength of light that you use, but you can get photocurrent densities near unity in the plateau region. So pretty much all of the photons that it absorbs efficiently generates charges that the electrons can be easily extracted by the electrode to the platinum counter electrode and drive water reduction, and the holes very efficiently oxidize water. Okay, so titanium dioxide is an absolutely fantastic material for driving water splitting. We'll go into the details of why that is in a bit. But let's try and understand the charge carrier behavior in this system. What's going on? Okay, so if we start at really low potentials here, minus 0.1 volts, where if we look at this dashed line in terms of the light minus dark, it's essentially flat. Okay, there's no photocatalytic process happening, and we get pretty much a flat line. There's pretty much, this is on the long time scale here that I'm looking at. This is 100 milliseconds after a laser pulse. Okay, we're essentially seeing no long-lived charge carriers. Okay, at 0.3 volts, where we start to see a little bit of photocatalysis, we see some long-lived charge carriers. Okay, at 0.7 volts, even more. 1.5 volts, even more. Okay, so essentially, on the 100 millisecond time scale after laser excitation, we see in the whole carrier region something that's pretty much proportional to the photocatalysis we see here. Okay, so we can relate what we see spectroscopically to what we see by what we see when we measure it using a potentiostat. So here, this is essentially just the kinetics of these traces. Before, I was just showing you spectrally what was going on at 100 milliseconds. Here, this is kinetically what's going on from the microsecond to the second. And we can see at these low applied potentials where we're not seeing any photocatalysis, so 0.1 volt and 0.2 volts, we see this pretty much, it recombines by the millisecond, the signal, and there's no really long-lived states, okay? Whereas at 0.35 volts and above, we see this longer-lived component from the millisecond to the second, okay? So we can start to see now by looking at what we measure here and what we measure using pump probe spectroscopy, we can start to understand what's going on. Because we know that these kinetic traces, which are, I'm looking at the whole carrier region now at around 500 nanometer light, we can start to understand, oh, this part here, that's probably related to the catalysis part. That this eventual decay is because these holes are reacting with water. And we can then study other materials using these same techniques. So hematite is a really popular material because it can harvest so much more light than titanium dioxide. So initially we studied titanium dioxide. Yeah, that was Fukushima and Honda. They showed everyone, look, titanium dioxide can do amazing things, but because it can only harvest 3% of the solar spectrum, people thought, well, you're really, really limited into how much hydrogen you can produce with this material, because you can only use about 3% of solar photons. So what about hematite, which can absorb a lot more solar photons, around 20% or so of solar photons? So theoretically, you can get, maybe 7 or 8 times more efficiency with hematite if it was to harvest all of those solar photons well compared to titanium dioxide. But unfortunately, it's not. It's not harvesting them well because it has some intrinsic limitations. How am I doing for time? Sorry. Okay, I'll get a move on. So this is the current voltage curve of hematite. What we can see versus the reversible hydrogen electrode, we only start to see photocurrent at around 1 volt versus RHE, whereas titanium dioxide was showing it 0.8 volts earlier. Okay, so that's again one intrinsic limitation of the material. It's not simply because it has a more positive flat band compared to titanium dioxide. It has major issues with charge transport and recombination. Okay, but you can get much higher photocurrent densities in titanium dioxide. Okay, because it can harvest much more light. Okay. Here we're probing on the ultra-fast timescale this time, the whole carriers, and we can see that from the femtosecond up to the picosecond, it doesn't matter what voltage you apply to this system, you're going to get this ultra-fast recombination component. Okay, you can't prevent it. And on the slower timescale here, the red curve is just following on from here at higher applied potentials. Here we see much higher photocurrent. We see this biphasic behavior. Whereas at 0.8 volts over here, we just see this single phase behavior. Okay, so we do get some relatively long-lived charges at 0.8 volts, but it just doesn't function. So whatever we're seeing here is again a recombination component, but it's a slower form of recombination than is occurring here. Okay, which has been studied in a later study, but I won't go into detail here. Essentially, you can see there are different types of recombination that can occur on different timescales. And what we see here at 1.4 volts is that we see again biphasic behavior, because again we have this recombination term, but we start to see this catalysis term here from around 10 milliseconds onwards. Okay, and this is where hematite can oxidize water. Again, this is maybe 10 times slower than what happens in titanium dioxide. So people have tried to improve the performance of hematite by doing lots of different things. So you can nanostructure it to minimize the distance that these photogenerated charges have to travel to then oxidize water. You can dope it with silicon to improve the conductivity of these charges. You can do a whole bunch of different things. But essentially, we're here in terms of performance, around 3.5 milliamps. I think there have been other studies that have reached about 4 now, platinum doped hematite, I believe. But we're nowhere near the limit, which is around 13 or 14, if I remember correctly. Okay. Oh, it's around 13. Okay. So this is annoying in a way, but that says hematite here. So if we look at all of the different materials, we can see that titanium dioxide, in terms of the record photocurrent it can achieve versus its theoretical, we can see a ratio of around 90%. Okay. So it can really well separate those charges that are formed when light interacts with the material. They can travel to the surfaces that they have to react, and they have good catalytic efficiency. So there are very few losses in titanium dioxide, but it's hugely limited by its very wide optical band gap. Then hematite, there are much bigger losses because of the difficulty poor charge transport and so forth, and poor catalytic efficiency on the surface, and we can only achieve roughly a third of what is theoretically possible. But recently, bismuth vanadate, like I say, is relatively new compared to hematite and titania. So that was studied in the 70s, and hematite they started studying in the 80s, and bismuth vanadate was studied in the early 2000s. It started to get popular. So this is relatively new material, can achieve around 2/3 of the efficiency. And when you form a heterojunction with tungsten trioxide to help spatially separate those charges, you can achieve around 90% of what's theoretically possible. So what happens in bismuth vanadate? So this is just a study of bismuth vanadate alone. Essentially what we see mirrors strongly in hematite, but just with a lower recombination term. So as you increase the applied potential, you move away from just a recombination term here to this other term here where we have a catalysis term plus some recombination component. But when you then couple it to tungsten trioxide, that initial recombination term becomes much, much lower. And what we see is just a long-lived term here at higher applied potentials, and then catalysis from the milliseconds onwards. And this is just showing you what the champion material looks like in terms of its architecture. This is these nanorods, these tungsten oxide nanorods, that have then been conformally coated with bismuth vanadate, and it has a surface co-catalyst on top to help promote water oxidation as well. So that can achieve near unity quantum efficiency. And I just wanted to highlight here that this whole concept of using a heterojunction to help spatially separate charges, it's something that already happens in nature. For example, in photosynthesis system 2, when you have light absorption by your chlorophyll, you have this whole system of like redox cofactors which transfer the charges to the catalyst, which drives water oxidation. And by separating these excited states, you prevent their ability to come back and recombine. Okay, so here we can see by using a heterojunction, we are paying a penalty of some potential energy losses or photovoltage losses by using a heterojunction, but we gain lifetime. So it's everything has a price, but in this particular system, it's worth paying that penalty because you essentially get something that's performing with near unity efficiency. So I wanted to go on to another type of spectroscopy that can help us understand charge carrier behavior. It's called photo-induced absorption spectroscopy, or PIA. So it's similar to TAS, but instead of using a very short pump and then probe technique, you use continuous wave photoexcitation this time over a period of several seconds to excite your material. And then you turn that light off for several seconds to see what the dissipative reaction of those charge carriers do. Okay, it's been used to study these materials and help us understand the rate law behavior, okay, and reaction kinetics for water oxidation and for cuprous oxide water reduction. So this is these are some typical profiles that you can get from the system. Here we're studying titanium dioxide again. We're holding a relatively high applied potential where we get, like I said to you before, we get really good photocatalytic activity and few losses. Okay, and here, when the light's turned on, we start to get a very sharp change in current transfer. Okay, so as soon as the light comes on, we start to see photocurrent, which is due to water being oxidized because electrons are flowing around your system. Okay, oops. But then we have a much slower rise in the hole carriers. So we're looking at the holes here. I didn't make that clear before. So here we're looking at electron flows through our potentiostat, and here we're looking at spectroscopically using 500 nanometer probe light to look at our hole carriers. Okay? But we see a much slower rise in the hole carriers, and they eventually reach this steady state. Okay? And when we turn the light off, we see a very slow decay of these holes as they dissipatively react with water, but a very sharp change in what the potentiostat measures in terms of current flows. Okay, so what we can do is we can look at these steady state regions, okay, and try and understand what's going on. So if we look at the power of our excitation source to drive this photocatalysis, okay, here, and we look at the photocurrent density, we see a near linear performance. Okay, so as we linearly increase the power of our light source, we get a linear increase in photocurrent. Okay, that makes sense. But we see this non-linear change in the steady state formation of holes. Okay, what does that mean? Let's make a model to try and understand it. Okay, here I have this sort of nano flower because it's based on a paper which studied cauliflowered hematite. Okay, the particular structure that we're looking here in, for the example of titanium dioxide, is a flat titanium dioxide material, but the explanation serves its purpose anyway. So if we want to understand what's happening in terms of the change in the whole carrier concentration with time, we need to understand, firstly, that this balance between flow of charges out the system, the photocurrent here, the electrons essentially going this way, and the flow of holes this way. So because of these processes, the flow of holes to the surface, okay, the reaction of those holes with water, which we can give this simple expression, a rate constant for that oxidation term, multiplied by the concentration of holes to some order of the reaction here. We're essentially getting a flow of electrons into the system as this reaction occurs, and then out of the system here, which is the photocurrent. Okay, so the rate of change of the holes with time must be balanced by the flow of electrons out of the system minus this reaction. At the steady state condition, these terms have to be equal because we're having no net change in hole carriers. Okay, here the change in hole concentration with time is flat, so we're getting, it should be 0. So these two terms then become equivalent at the steady state region, and then we can just log both sides and do funny things. And then what we'll see is that if we do a log-log plot of the photocurrent versus the whole carrier concentrations, which we can measure spectroscopically, and this can be measured using a potentiostat, then we'll get a line, and that intercept of that line can give you the water oxidation constant KWO, and the slope of that line will give you the reaction order beta. And that's what I did here at a range of different pH. So I studied the reaction in acidic, neutral, and alkaline pH. And I saw that in alkaline pH, the slope of the reaction was 3, okay, which was it was approximately 3, which told me that the rate limiting step in this water oxidation process occurs on the third hole transfer, whereas in whereas in neutral and acidic pH, that rate limiting step occurred when beta was approximately 2. Okay, so what we see is that on titanium dioxide, we get a slight change in the reaction mechanism depending on the pH in the system. And what I did is I speculated what was happening in acidic pH and alkaline pH. So here, if we just look at the surface of titanium dioxide, for example, we could have a hydroxylated surface which accumulates 2 whole carriers. Okay, this is the second. So this is looking at the acidic region. So the rate limiting step is due to the second transfer of holes to the surface, and then we can have a deprotonation stage, which is the rate limiting step in acid, but in base that may not be the rate limiting step because deprotonation by the higher concentration of alkali of OH minus ions instead might make this process instead the breaking of this titanium oxy titanium cycle, that could be the third rate limiting step. But again, this is just speculatory on my part. I think what's really interesting though is that despite this change in mechanism, if we look at the actual turnover frequency of holes at one sun in acid, neutral, and alkaline pH, they were all almost identical, okay, which I thought was really interesting. So I think that's why people say titanium dioxide, it doesn't matter which pH you measure it in, you're going to get the same performance. And it's just pretty much because at one sun, you're at that region where these different slopes all intersect at one sun conditions, and that will change at much higher suns. Then we can use this to understand wide range of different metal oxides. Okay, so these are the different metal oxides that have been studied, that we've studied. And we can see that they all have different valence band energies, okay, and of course different conduction band energies too. But essentially what we see here by doing photo-induced absorption spectroscopy and looking at the different turnover frequencies versus the concentration of whole carriers, that we are towards the left if we have a much deeper valence band, okay? And what that essentially means is that the rate constant for water oxidation is much, much higher, okay, as you have a deeper valence band. So we essentially measured all of this stuff, we plotted here, and we saw, oh, hematite is quite far on the right, so it's slowly oxidizing water for whatever reason. Bismuth vanadate, it's similarly slow. Titanium dioxide is here, and tungsten trioxide is over here. And then it occurred to us, oh, this is simply tracking the valence band energy. And what we see here is, and when you have a very deep valence band versus the water oxidation potential, you have a huge overpotential in tungsten trioxide for driving this reaction versus, say, hematite. Okay, yes, there is a large overpotential in hematite for driving this oxidation of water too, but this is neglecting potential losses due to trap state formation and things like that. Okay. And then if we look at the transient absorption spectroscopy, back to what I was telling you before, these are the kinetic traces of these whole carriers. And we see here, hematite is really slow. Bismuth vanadate here, similar, I guess, to hematite. Titanium dioxide. And then tungsten trioxide is much, much faster in terms of its water oxidation rate constant. We see here by 10 milliseconds, all of those whole carriers have been transferred to water. And that's it. That's an overview of all of the different techniques we use essentially in the Durant group and that have been developed there and that I learned from his group, and just a bit of a summary of the about how we can use those spectroscopies to understand photocatalytic processes. Thank you.